Welcome back. In Part 1, we explored air masses and the main types of fronts. Now in Part 2, we'll focus on frontal weather hazards, real-life scenarios, and how to use charts and forecasts to stay ahead of the conditions during flight. Let's begin with frontal hazards. The biggest risks when flying near fronts include turbulence, wind shear, icing, reduced visibility, thunderstorms. Each hazard varies depending on the type and strength of the front. Cold fronts move fast and tend to generate convective activity, such as towering cumulus and cumulonimbus clouds. These bring heavy showers, strong gusts, and moderate to severe turbulence. If the cold front is unstable and humid, embedded CBS can occur. These are dangerous because they're hidden inside stratiform clouds and can surprise even IFR pilots relying on radar alone. Now let's talk about wind shear. When cold air undercuts warm air, surface winds can shift rapidly. Approaches during frontal passage may include sudden changes in wind speed and direction, especially near the runway. This is particularly critical for final approach. Wind shear can lead to ballooning, hard landings, or go-arounds. Always brief wind shear escape procedures when a front is in the area. Warm fronts, in contrast, bring more layered clouds, steady precipitation, and low ceilings. The main risk here is prolonged IMC, bad for VFR operations and challenging for IFR due to icing and poor visibility. Ice can form in stratus or altostratus layers along a warm front, particularly between 0 degrees Celsius and -15 degrees Celsius. You may pick up rime or mixed ice even without active precipitation. Watch OAT and activate anti-ice systems early. Now let's talk about occluded fronts. These can combine the worst of both warm and cold fronts, layered clouds, embedded thunderstorms, and sudden temperature changes. Conditions are often highly variable. In occluded fronts, cloud layers may stretch from surface to tropopause. Expect reduced climb performance, moderate to severe turbulence, and visibility issues at multiple flight levels. Let's walk through a flight planning example. You're flying from Amsterdam to Milan. The forecast shows a cold front over southern Germany with CBS, hail, and strong winds. You might choose a more western routing plan for extra fuel in case of reroutes. Monitor SIGMETs and radar trends closely. Be ready for deviation requests in flight. Always check surface analysis charts to spot fronts before departure. Then compare with significant weather charts to see their forecasted evolution. This helps you avoid areas with embedded weather or turbulence. Speaking of charts, here's a breakdown. Surface analysis shows actual frontal positions. Prog charts forecast future movement. SIGWX, significant weather charts, show areas of turbulence, CBS, and jet streams. Combine these for full situational awareness. Let's now look at front movement speed. Cold fronts typically move at 20 to 30 knots. Warm fronts move slower, around 10 to 15 knots. This affects how long you'll spend in weather and when you'll enter or exit the affected zone. When planning IFR flights, always check TAFs for each airport along the route. Look for FRQ TSRA, SHRA, or BKN 008. Wind shifts over time. Prob 30 or tempo groups. These give clues about frontal impacts. PIREPs are also key. They give real-time reports of turbulence, icing, and ceiling conditions. Use them to validate forecasts and make adjustments before and during the flight. Now let's talk about pressure changes. As a front passes, pressure drops rapidly ahead of a cold front. Pressure rises sharply after passage. Pilots should monitor the altimeter and reset to QNH regularly during frontal crossing. Also expect temperature shifts. Crossing a warm front might bring an increase of 5 to 10 degrees Celsius. Cold fronts. A sudden drop. These shifts affect engine performance, icing potential, and even passenger comfort. Frontal zones often include cloud layering. You might encounter low-level stratus, mid-level altostratus, high-level cirrusol stacked over the front. Each may include moisture or turbulence. Plan altitudes accordingly. Let's work through a descent case. URI descending through a frontal zone with layered clouds from FL 150 to 5,000 feet. Ice begins forming at -4 degrees Celsius. Switch on anti-ice inform ATC if climb or reroute is needed. Maintain visual scan and expect variable visibility near the base. Another scenario, flying through a warm front, you're in IMC with 3000 m visibility and drizzle. Your alternate airport also lies under the same frontal band. Review alternate minima. Add holding fuel. Brief crew for low-vis approach and missed procedure. Frontal systems also cause mechanical turbulence over terrain. When stable air from a warm front flows over mountains, expect mountain waves, rotors, and wind shear even without CBS. Let's recap what we've learned. Cold fronts equals turbulence, gusts, CBS. Warm fronts equals low vis, steady rain, icing. Occlusions equals mix of both, complex and changeable. Stationary fronts equals persistent low clouds and precip. Planning equals charts plus PIREPs plus alternates equals smarter flights. In the next episode, we'll wrap up the frontal weather series with real case studies, ATC coordination tips, and advanced planning techniques. See you in Meteorology number 39, Air Masses and Fronts, Part 3.